Hello everyone. I hope you are safe and healthy. So this video is in continuation to our last video, which was on the introduction of differential equations, and then we also talked about the separable and the linear kind of differential equations. We also covered a couple of examples in the last video. In this video, we would be talking about another type of ODE, which is exact, and another type which is homogeneous linear differential equations. So I hope you have already gone through the blog. Let's talk about the exact differential equation. The format for the exact differential equation looks of the kind. So I'm going to place a heading of exact differential equation. So that's going to look of the type m of xy uh, dx plus n of xy dy is equal to 0. So m of x comma y and n of x comma y are the two functions of x and or x and y or x or y. It doesn't matter, but even if both are available, that's not going to be a problem. So this is the format of the exact differential equation. It should be of this kind. And along with that, there is a necessary condition that the partial differentiation of m with respect to y. So if m is with dx, so we have to take the partial differentiation of m with y. So that's opposite. And that should be equal to the partial differentiation of n with dx. So this is a necessary condition for the above equation to be exact. So this is something which we have already uh, covered in the blog post. So let's talk about a few examples. So the first example is 2x y cubed dx plus 3x square y square dy. This is equal to 0. So since the format is matching, so we are going to label the mxy first and nxy first. So m is 2xy cube and n is 3x square y square. Now we have to first verify whether this is exact or not. So we are gonna find the derivative of m with respect to y. That's gonna come as 2x would be treated as a constant, and the differentiation of y cube will be 3y square. So that's gonna come as 6xy square. And likewise, we are gonna differentiate n with respect to x. So it's gonna come as 3y square would be treated as a constant, and x squared differentiation is 2x, so that's going to come as 6xy squared. Now since dm over dy and dn over dx are equal, it means that this particular equation is exact. So if this is an exact differential equation, we have to find a function f such that its uh, derivative with respect to x is equal to the one which is associated with x, that is equal to m. So df over dx must be equal to m, which is 2xy cube, and df over dy must be equal to n, which is 3x square y square. So using these two equations, we got to find the function f, and once we find that function f, the solution will come in the form of f of xy is equal to c, where c is an arbitrary constant. So let's talk about this. Let's talk about how to solve this. So we have df over dx given as 2xy cube. So we are going to integrate both sides. This can also be written as df is equal to 2xy cube dx. So we are going to integrate both sides. So f, which is a function of x and y, is going to come as, now 2y cube will be treated as a constant. So integration of x with respect to dx. So that's going to come as 2y cube is as it is, and x integration will be x square over 2. Now be careful that had this was an integration of just one function, we would have added a constant of integration, which is just c. But since this is an integration with respect to x, but there is already a y in it, so the constant of integral will not actually be a constant, that will rather be a function of y. So we are going to add by as the integration function which we are going to get after the integration of this particular expression. So finally, we are going to get f of xy as this 2 and 2 gets cancelled, and we are left with x square y cube plus by. But we cannot leave the answer like this because we got to find the value of by. So we are going to use the other equation now, since we are also given that f over dy is 3x square y square. So let's differentiate this equation. Let's differentiate this equation with respect to y and get the value of df over dy. So if we are going to differentiate this once again with respect to y now, we are going to get definitely we are going to treat x as a constant. So the differentiation of x cube is 3y square, and the differentiation of by is b dash y. And we already have an equation of df over dy over here. So we are going to compare both and get the value of by. So we are going to write that uh, 3x square y square plus b dash y. This should be equal to df over dy, which was on the previous page, which is 3x square y square. So these two terms get cancelled and we get the value of b dash y as 0. Integrating both sides, so b dash y will become y. Integration of 0 is 0, plus we add a constant of integral c1. So we get the value of by as c1. And now we already have the value of by1. That one we can plug in this particular equation to get the final value of fxy. So if we plug this in, we get the value of fxy as x square y cube plus c1, because the value of b1 because the value of by is c, and since the equation is of the form uh, if xy is equal to c, so we are going to rewrite the final answer as x square y cube plus c1 should be equal to c, and both the constants can be merged together. So we can write that x square y cube is actually equal to another constant c2. So this will be the final answer for this particular exact differential equation. Let's talk about another problem. So this one is y plus 1 over x dx plus x plus 1 over y square dy is equal to 0. So first, as usual, we are going to locate what m and n is. So m is y plus 1 over x, and n is x plus 1 over y square. So we're going to differentiate m with respect to y first to see whether this is exact or not. So differentiation of m with respect to y is 1 because x would be treated as a constant, and likewise the differentiation of n with respect to x is also 1 because y would be treated as a constant. Since both are equal, this means that the given equation is an exact differential equation. Now we are going to find a function f such that df over dx is equal to y plus 1 over x, and df over dy is equal to x plus 1 over y square. So as usual, this time we are gonna let's start with this one. Let's integrate this and use the other one later to find the final function, because in the previous question we used df over dx. So let's do this one with df over dy. So our df over dy is given as x plus 1 over y square. So we're going to integrate both sides with respect to y. So we are going to get the function f of xy, as this will become x times y, and integration of 1 over y square is minus 2 times integration of, or let's write it in the two steps. So f is going to be equal to integration of dy plus dy times y raised to the power minus 2. So that's going to come as xy plus this will become y raised to the power minus 1 over minus 1 plus. Now since the integration is in terms of y, but since the function has an x as well, so we'll have a constant of integration as a function of x rather. So fxy is this. So this can be simplified as xy minus 1 over y plus ax. Now we got to find the value of ax. So we are going to use the other equation, which is df over dx is equal to y plus 1 over x. So let's differentiate this with respect to x. So when we do that, we have differentiation of f with respect to x is y would be treated as a constant. So this will be y plus a dash x. But we already have the value of df over dx as y plus 1 over x. So this shall be equated to y plus 1 over x. So this y and y gets cancelled. So we get the value of a dash x as 1 over x. So if we are going to integrate both sides to this equation, so we'll get the value of ax as integration of 1 over x is natural log of absolute value of x plus a constant of integration as c1. So we got the value of ax, so let's plug that in over here and get the final value of fxy, and let's equate it to c as well. So since f of xy is equal to c is the final solution, so we are going to write that xy minus 1 over y uh, plus natural log of absolute value of x plus c1 is equal to c, and both the constants can now be merged. So it can be finally written as xy plus natural log of x minus 1 over y is equal to a constant c2, which is the final answer. Let's talk about another example on the same kind. So this one is, we have 2x cos y plus 3x square y dx plus x cube minus x square sin y minus y dy is equal to 0. So as usual, we are going to first write what m and n is. So we already know that this particular expression is going to be m and this particular expression is going to be n. So if we differentiate m with respect to y, we're going to treat x as a constant. So we'll get 2x, and the differentiation of cos is minus sign. So we have minus sin y plus we have 3x square, and the differentiation of y now over here is 1. Differentiation of n with respect to y is going to be, x would be treated as a constant, so that's going to be 0 minus the x square would now be the sin y would be treated as a constant, and the x square is differentiated as 2x, and the differentiation of y over here will turn out as this actually should be differentiated with respect to x. So when we differentiate n with respect to x, then the differentiation of x cube will be 3x square. Sin y would be treated as a constant, and differentiation of x square is 2x. So both of them are equal to 3x square minus 2x sin y. This is also equal to 3x square minus 2x sin y. So since both are equal, it means that this particular equation is exact. So we are going to find a function such that df over dx is equal to 2x cos y plus 3x square y, and df over dy is equal to x cube minus x square sin y minus y. Let's take anyone and start integrating it. So if we are taking df over dx, which is equal to 2x cos y plus 3x square y, so the integration would be the function of f of x y would be, since y would be treated as a constant, so 2 cos y comes outside, and the integration of x is x square over 2. Likewise, 3y would be treated as a constant, and integration of x square would be x cube over 3. And we have to insert after integration, rather than inserting a constant of integration, we have to insert a function of integration, which should be a function of y. So that's going to be f is equal to simplified version would be x square cos y plus x cube y plus by. So as usual, we are gonna differentiate this now in terms of y so that we can equate it from this particular equation. So let's differentiate this with respect to y. So df over dy is going to be, x would be treated as a constant. So that will be x square minus sine y plus x cube plus b dash y. So this is nothing but negative x square sine y plus x cube plus b dash y. Df over dy now should be equated to the expression which is over here, which is x cube minus x. So let's equate it to x cube minus x square sine y minus y. So this x cube and x cube gets cancelled. Negative x square sine y and negative x square sine y gets cancelled. So we are left with b dash y is equal to negative y. And if we integrate both sides, the value of by comes as negative y square over 2 plus a constant of integral as c1. Now, since we got the value of by, let's plug that in over here and get the final function. So the final answer will look like fx comma y would actually be equal to x square, uh, that was x square cos y plus x cube y. Over here we have uh, x cube. Over here we have x cube y and plus by, which is negative y square over 2. So this is negative y uh, square over 2 plus the constant of integral c1. This is actually equal to c. So finally, the equation comes out as x square cos y plus x cube y minus y square over 2 is equal to c2, which is the final answer. Let's talk about another question on this. So this is a little bit different, although based on the same concept. So we have to determine the value of a such that 2x over y square plus y cos xy minus 3 dx plus ax square over y cube plus x cos xy dy is equal to 0. We have to find the value of a such that this equation is exact differential equation. So the concept remains the same. We have to locate m, which is over here, and we have to locate n, which is over here. So we got to differentiate dm. We got to differentiate m with respect to y, treating x as a constant. So that's going to come out as 2x, and differentiation with respect to y of y raised to the power minus 2. Over here, we got to use the product rule. So y cos xy would be using product rule, and the differentiation of negative 3 is just 0. So that's going to be 2x minus 2y raised to the power minus 3 plus y remains as it is. Differentiation of cos xy with respect to y is going to be minus x sine xy plus cos xy. So this is finally coming as negative 4x y raised to the power minus 3 minus xy sine xy plus y cos xy. Now we're going to do the same activity with n, and we are going to differentiate that with respect to we are going to differentiate n with respect to x. So differentiation of n with respect to x, treating y and as a constant. So that's going to be d over dx of x square, d over dx of x square plus d over dx of x cos xy. Uh, so that's going to be a over y cube. This is going to be 2x plus we are going to use the product rule. So the first term is as it is. The differentiation will be negative y sine, since y is treated as a constant. So negative y sine xy plus cos xy. So this is equal to 2ax over y cube uh, minus xy sine xy plus x cos xy. So dm over dx and dm over dy and dn over dx must be equal. So let's write both the figures now. Minus 4 x y raised to the power minus 3 minus xy sine of xy, and the last expression is plus y cos xy. Now this must be equal to 2a y raised to the power minus 3 minus xy sine xy plus the last term is x cos xy. If you notice carefully, uh, these two expressions get cancelled, uh, and we got to make one small correction over here. When we are taking the first term out, so over here the parentheses is going to close over here. So this won't come and the y won't come over here. That's one. And likewise, the parentheses is going to close uh, over here. So this expression also won't have any x. So y won't come here and x won't come here. So if this is the case, then these two terms are also cancelled. So this results in minus 4x y raised to the power minus 3, and there's an x over here as well. So this is equal to 2a x y minus 3. So if we compare both, the value of a comes out as minus 2, which is the final answer. All right, so we have talked about the four different varieties of the exact differential equation. Now let's talk about the homogeneous differential equation. So in homogeneous, we have already gone through the general format of the homogeneous linear equation and how the solutions look like when the homogeneous equation is of second order. So let's talk about the first example. We have 2y double dash minus 7y dash plus 3y is equal to 0. So over here, we will first write the characteristic equation, which is 2r square minus 7r plus 3 is equal to 0. So the best way to remember this is just replace all the derivatives, all the derivatives. So this is of second order. So we are gonna put square over here. This is first order, so we are gonna put 1 as a power, and this is of 0 order, so we are gonna just write the constant and nothing else. So we will find a solution of this differential equation. So let's split the middle term. So we are gonna write this as 2r square minus 6r minus r plus 3 is equal to 0. From the first two terms and from the last two terms, we are going to take a common factor. So it's 2r, r minus 3, and over here we take minus 1 as a common factor, so it is r minus 3. So r minus 3 is taken as a common, so we are left with 2r minus 1. This is equal to 0. So the value of r comes out as 3, and the value of r comes out as 1 over 2. Now, since the solutions are distinct, hence our final answer is going to look like C1 e raised to the power, the first root, which is 3. So along with 3, we have to put x. And the second root is 1 over 2. So that will be C2 e raised to the power 1 over 2x. So that's going to be our final answer for this particular question. Let's talk about the second question. So we have y double dash plus 3y, y triple dash rather, y triple dash plus 3y double dash minus 10y dash is equal to 0. So the characteristic equation is going to look like r cube plus 3r square minus 10r is equal to 0. We're going to take r as out, so we are left with r square plus 3r minus 10 is equal to 0. Let's factorize the middle, factorize this particular expression. So r square plus 5r minus 2r minus 10 is equal to 0. So that's going to look like r minus 2, r plus 5 is equal to 0. So the roots are all distinct, which are 0, 2, and minus 5. So the final answer is going to look like y in terms of y as a function of x is C1 e raised to the power 0x plus C2 e raised to the power 2x plus C3 e raised to the power negative 5x. So that's going to look like, let's shift this a little bit over to the left. So that's going to finally look like, since e raised to the power 0 is nothing but 1, so it's C1 plus C2 e raised to the power 2x plus C3 e raised to the power negative 5x. So this is the final answer. Let's talk about another one. So this one is y double dash plus 2y dash plus y is equal to 0. So the characteristic equation is r square plus 2r plus 1 is equal to 0. This can also be written as a perfect square, r plus 1 whole square is equal to 0. So the value of r is just minus 1. It means that the roots are repeated. So the final equation is going to look like c1 plus c2x e raised to the power, the root is minus 1, so we're going to write minus of x. So that's going to be the final answer. Let's talk about another one. So in this case, we have y double dash plus 2y dash plus 5y is equal to 0. So the characteristic equation is r squared plus 2r plus 5 is equal to 0. Let's use the quadratic formula to get the value of r. So that's minus 2 plus minus square root of 4 minus 4 times 1 times 5 over 2 times 1, which is just 2. So it's negative 2 plus minus 4 minus 20 over 2. So that's going to look like negative 2 plus minus root of negative 16 over 2, which is nothing but negative 2 plus minus 4i over 2. And this can also be written as r is equal to negative 1 plus minus 2i. So if we notice these are complex roots, so the equation is gonna be C1 uh, cos, the number over here is 2, this is the imaginary part, so 2x plus C2 sine 2x, and this should all be multiplied with e raised to the power minus x, because there is a minus 1 over here. So this will be the final solution of this particular differential equation. So that's it for this blog. We have covered good examples about the exact and the homogeneous linear equation, especially of the second order. So I hope after reading the blog and this video, you get some confidence about how to solve such questions based on such topics. So next time, please take care. And there's also a link if you want to schedule a free tutoring session with me. So do check that out, reserve a slot, and I look forward to meet you. So bye bye, take care, and see you in the next video.